Hey guys, welcome back to lesson 3, position and displacement. In today's lesson, we are going to determine how position, distance, and displacement are related. So to do so, let's think about the following scenario. In stock car races, drivers often travel very large distances, usually 500 miles or more, but the displacement is actually very small, usually a couple feet. So why do you think that may be? Let's think about that before we move on. So in the last lesson, we learned the rules for determining the amount of significant figures there are in any given measurement. In today's lesson, we'll correctly use significant figures in our calculations and determine how many significant figures should be in your final answer. We'll also differentiate between vector and scalar quantities, as well as differentiate between distance and displacement. So let's say you have some measurements that you came up with in the lab, and you wanted to find the sum of these measurements. Well, if we were adding these values up together, we could see that there is differing amounts of decimal places in each of them. Right? What that leads us to do when adding these together is line up the decimal, and essentially we will add these imaginary zeros as placeholders. In science, when adding these up together, we actually do not know those places. We are uncertain about their value. So therefore, our final answer should have as many decimal places as our addend with the smallest amount of decimal places. So that is this number right here, 3.22. That has 2 decimal places. So oftentimes students will ask, when they get this large number, 17.6163, how do I know where to round this number? Well, that's your answer right there, right? Our least precise measurement had 2 decimal places, so therefore our final answer should also have 2 decimal places. So our final answer is 17.62 centimeters. So how about if we are multiplying or dividing and determining the amount of correct significant figures we should use? So in this example, we have 4 significant figures in our first number, and we have 2 significant figures in our second number. We multiply these numbers, we get this long number here, 8.5344 centimeters squared. However, our final answer cannot be more precise than our least precise measurement, right? Our least precise measurement here has 2 significant figures. Therefore, our final answer should also have 2 significant figures. So our final answer would be 8.5 centimeters squared. So let's look at another example. In this example, our least precise measurement has 3 significant figures, right? That's this one right here, 20.0. This 0 is also significant since it's following that decimal. So therefore, our final answer should also have 3 significant figures. This decimal has to be included to tell us that these 2 leading zeros are significant. Let's look at another example. In this case, the answer is rounded back to 2 significant figures because in our problem, our least precise measurement has 2 significant figures, this 22 centimeters here. So in this case, that decimal would be omitted. All right, so let's have some practice with this. Go ahead and pause the video now and perform the following calculations, and make sure that you include your final answer with the correct amount of significant figures. All right, so we have a video embedded here. I love the game Angry Birds. I don't know about you guys, but it was very addicting. And little did I know that it was actually teaching me physics concepts. So let's go ahead and watch this video now and then answer the following questions. What is the difference between a scalar and a vector quantity? Let's try to give an example of each. And then do your best to identify if these are scalar or vector quantities. So length, time, displacement, acceleration, so on and so forth. Which ones are scalar quantities and which one are vector quantities? Now that we finished watching that video, how did you do in identifying which ones were scalar and vector quantities? And what do you need to remember in the future about scalar and vector quantities? Okay, so when we study how an object moves, it may be helpful to include a number line to help us visualize that vertical or horizontal one-dimensional motion. We can determine or choose a starting point, what we call a reference point, and that will help us to determine if our object actually changed its position. So what is the difference between distance and displacement? Well, distance refers to the magnitude or the amount that object traveled. That doesn't necessarily tell us which direction the object traveled. So for example, let's say you drove 50 kilometers, right? That's not telling me which direction you traveled in. So to do so, if I wanted to know which direction you traveled in, you would have to give me some frame of reference, and you would also have to give me some direction. It can be north, east, south, or west. And if I wanted to put this on a number line, that would tell me if you went in the positive or in the negative direction. So let's go ahead and use these vocabulary terms, vector and scalar, to describe these two concepts, distance and displacement. Right? So distance and displacement. One of them is a scalar and one of them is a vector. Okay, so let's take a moment and revisit that question that we led off this lesson with. Using what we've learned so far, explain why the distance of the race car drivers was more than 500 miles, but their displacement is very close to zero. We have another support video here that you guys can watch and take notes to the right. This video goes a little more in depth in using a number line to determine position. All right, so you guys are doing so amazing. Let's make sure that we're all on the same page. So let's go ahead and answer the following questions. So in conclusion, today we learned about vector and scalar quantities and how they relate to distance and displacement. In the next lesson, we are going to use what we learned today and determining how fast an object can move and what we call average velocity.